Hello, hello.
Hello, hello.
Oh, goody. I can hearing you.
Who's
Okay,
this?
I'm going to mute. And oh, Dave,
Yeah.
you in particular, the things you wrote on the thing recently, I think is absolutely first class.
Well,
Your
thank you.
comments about the stuff out there. I'd give you 5 thumbs up, but I've only got 2.
I accidentally put it on the second time because I didn't see it the first time. If it got posted, so thank you.
Oh, I was wondering about that. Gmail has been a real pain in the left ear lately.
It's good to see all you. Hi, Ness there. He was there. There you are, Kevin. What you eating? What you got for us to eat tonight?
Chicken pot pie and a fortified limeade.
Ah. Someone has control of us. Let's see. Oh, okay. No, we're good. Someone's playing with a mouse there. I'm trying to see all that stuff in the background and Mark Schaefer stuff. He's got a lot of stuff in the back, a lot of technical things back there. Looks like. And let's see, Polly K's coming on. And Joe's muted, and Jack is muted. The logo looks terrific on my screen. And Kevin, you've just turned into a nebula. Actually, I can give myself a background of the comment here. Let's see here. Oh, there we go. Looks more like it. Hey, Joe, there you are. Unmute. It's on the bottom left-hand corner of your screen. Just click on it.
I know how to unmute. I guess we could mute back up once the thing starts.
Yeah, I'm sure they're going to do it anyhow. Whoever's in charge.
I believe Spencer's going to mute us all.
Oh,
That's the plan.
Yeah.
I'm trying to see you.
Yeah, I'll mute if we have to. Yeah, this is great to hear all this chatter going on ahead of time. Sort of like being in person.
That's nice. I sure miss it, that's for sure.
Hey, Spencer, we have 25 people on and it's 15 minutes till the meeting's supposed to start.
We had people on at 7:10.
Oh, wow. Cool. I hope this is a success. We've done a lot of planning and I'm really, really happy to thank you to help us organize this.
I like the logo.
Yeah, it looks pretty good. I don't want to say any more than that because I don't want to start an argument, but it does look pretty good.
Yeah, comment on the logo. I'll drink to it as well.
Yeah.
Great. Is it good?
Getting hungry watching Kevin eat.
We didn't tell the membership to bring drinks for this general meeting.
That's okay. I just had a hot dog from Costco, so I'm okay.
Start video? Okay, I think I'm on.
There you go. Hey, the president has arrived. Hey, Curtis.
Hey,
I think I'm
Curtis.
here.
Good to see you.
Oh, Jack Eastman's on there too, huh?
Mm-hmm. Hey, Curtis, it's Greg. We've got 25 people on already.
I can't see anybody except the 4. I see 4 or 5 here. Am I supposed to see everybody?
You have to scroll down.
Oh, I have to scroll down? Wow. Let's see. Oh, I see Joe.
Hey, I see Tim. Hi, Tim.
Scroll down, right?
Hey, Joe.
Daryl. Hey, buddy. How you been? Good to see you.
Yeah.
A lot of people don't have cameras, apparently.
They're just hiding. They don't want you to see him. I'm looking for Jack Eastman. Does he have a camera?
Hey, Tim, it's Polly. Good to see you.
No, Polly.
Long time no see anybody.
Yeah.
Yeah.
Hermit, so now that we Zoom, I can be myself.
Yeah.
Okay, so if you have a little bar on the side with 3 or 4 pictures, you can grab the bottom left corner and pull it all the way out and see about 10 or 12 people.
Yeah, I
Oh.
can't bring it up here. I've got full screen, but I don't see. Let me look.
Yeah, if you at the top, there's a toolbar that'll let you view up to 9 people. But even then, there's a left and right arrow. You can scroll through panels and see everyone who
Yeah.
has video.
Yep.
Well,
Yeah.
Spencer is sharing the LAAS screen, and that fills up most of my screen. So I just have little windows off onto the right that I have to scroll through.
Right, that's right. That's how it's going to work.
Did I cut it in screen share?
Yeah, I got it. I did it. Oh,
Yeah,
yay.
go ahead, sure.
Well, I'm the one, I'm on the camera that says Janice.
Yeah.
Okay, so what I'm talking about is if you're seeing this and you can't see very many people on the side, you can grab this whole thing and pull it across like this. And then the more people I think that's everyone that's on right now. So the more people that get added, they might get filled in here and
29.
drop off the edge, but that's how you see it.
Arrow on your picture, and in the right top corner, you can change your name.
Hey, Daryl, do you have any idea when Mount Wilson's going to reopen to the public?
Next year, probably.
That's it, huh? Wow.
That's what that's what I've been hearing. That's what Tim's been saying, and I usually think that Tim has his finger on the pulse up there pretty well.
Yeah, we follow the guidelines for museums. And so as long as the county guidelines prohibit gatherings of people not from the same household, which they do, then Mount Wilson will not open to the public.
Can we tell them we're from the same household?
Yeah, we are, the LAAS house.
There you go.
Yeah, well,
Thumbs up, dude.
there are legal ramifications to worry about here, liability, all that good stuff.
Oh,
Hey,
well.
Simon, I haven't seen you for ages, dude.
There we go.
It was Daryl saying hello. Simon, you're muted. You have to unmute to talk.
Someone who put the Zoom on the? Are you guys seeing the Zoom logo on your main screen?
No. I see you.
Somebody was sharing their screen. Yeah.
Oh, okay.
Joe. Good evening, Joe. Good evening, Daryl. Good evening, Tim.
Hey,
There you go,
Simon.
Simon, you got your mute off. Very good.
Hello,
Joe, can we have it?
everybody. From Berkeley, California. Jack Eastman told us about the talk tonight. So Mike and he have known each other for forever, so we thought we'd join in too.
That's
There's Evan from Lockwood.
Hey.
Hey, Evan.
Hey there.
How you doing, man?
Pretty good. How are you?
I am doing well. It's nice to see your face, my friend.
Nice to see everyone.
Yeah.
Hey, Evan. Welcome.
That's mine.
Evan, good evening. This is Simon. Just noticed you're vice president now, right? I don't know how long that's been.
What?
Who?
Who?
Evan's not vice president.
No, I'm not. No.
I guess I saw the wrong thing.
Yeah. What
So
happened?
you up there for the meteor shower?
He was vice president, yes. Many years ago.
I'm going to there tomorrow night. I'm taking Phil up there tomorrow.
I might join you up there.
Good. Looks like
I was thinking about going up there as well.
Good. Nice to see you. It'd be
I'm gonna
great.
go out and come back.
Is that, are we just going to be open and masking?
Yeah. I'm bringing my. Me and Phil are bringing our chaise lounges, so we can just lay there and watch the
Great.
show.
Great.
Yep.
Cool. Hey, here's Greg, my website development partner.
Good. Yeah.
And I like your backgrounds, guys. Very cool. It's like you're all in outer space or something,
We are.
Yeah.
or from a different planet.
I'm on Mount Wilson.
Oh, good. Yeah, I see that. Yeah, that's very cool.
That's outer space.
Just by luck, I was getting ready to go to Tim's class to be a docent there, and the COVID hits and this gets canceled.
Ah.
That week. was.
That's a shame.
I will be back in a second, guys.
Okay.
Yep, we still got 5 minutes.
Okay, guys.
You
we've
will
got
be an
5 more minutes.
excellent ghost starter.
Say again, Spencer, garbled a little.
Actually, we'll get started in 5 more minutes. I see Jim just joined us. Welcome, Jim.
Kevin,
Hello.
I'm ready to go to sleep.
Me?
Look like
Yes, I'm.
yeah, you look totally relaxed.
Yes, I am.
Ready for the meteor shower tomorrow night.
Somebody who had made a comment about people being relaxed, and my response was, "Is it pants? Who's wearing pants?"
You don't want to know.
Don't stand up.
I won't.
Then we'll be out. Then we'll be out of. Then we'll be in outer space for sure.
Or spaced out.
Yeah, for sure.
Mark Schaefer, what is that next to you?
Hey, Daryl.
It's what?
What is what next to me?
What, or is that just your
Guys, can you
background?
hear me?
Is that your background picture? What's your background picture?
Oh, that's Perseverance.
Yeah.
Ah, okay.
Cool.
You look like a savior, Joe.
You guys can hear me?
Yeah, we can hear you.
Yes, sir.
So what's wrong with my background photo image?
Did you see the
What's wrong with it?
stuff behind the
Yeah.
halos?
Nothing's wrong with it.
There's something wrong. I just noticed.
It's just it's a zoom thing. Sometimes it has a little glitch, but
No,
You mean
what
it's-
glitch?
Oh,
What glitch? What
The
is
thing
that?
behind your,
I mean, it looks
the
like
thing
you're wearing
behind
a
your
turban.
head.
Huh?
Move your head. What's that look? What's that behind you?
yeah,
There you
see?
go.
There you go.
What's
Oh, I
wrong?
think
No,
it's a
there's something wrong.
shadow.
Nice.
The wrong
I think
color.
that's caused by shadows being behind
If
you.
you try to image this, you can never get this kind of image.
Hey, I want to congratulate all of you. First, I want to congratulate Evan for putting the scope out last night, but especially getting rid of the bat and the rodents and cleaning up
Yeah, way to
that
go.
area down there, and also getting the wires connected properly for the go-to. Congratulations!
Oh,
Great job, man.
that was not me. That was Al.
I know, but you were responsible for getting it going. You
And
were
no, I
responsible.
just did the cleaning, which I got a lot of practice in the service cleaning everything.
Yeah.
Well, we're grateful. Thank you. I think everybody.
Thank you, Evan. Thank you.
Yeah, a lot of people really enjoyed it at the family night there.
Yeah, everyone. I've seemed like everyone really liked it. I mean,
Yes,
look,
no question about it.
I took after. It was nice and clean, but we'll see how long that lasts.
Is it in inspection order?
I wouldn't count on a white glove inspection, but you know.
Spencer, are you going to mute everybody during the presentation?
Yes, I am.
And you might going to talk to them about the chat feature or the raising the hand?
Sure. Yeah, so yeah, there's a chat feature. Anybody familiar with it?
Mm-hmm. Well, everybody.
Reaction.
Who's giving away the door prizes tonight?
No door prizes tonight. Next week or next month.
Next month.
Oh, okay. Hey, congratulations.
Taking this one step at a time here.
Yeah, Greg, congratulations. Doing a great job with the scouts still, honestly.
Yeah, we got a report on that tonight. Really, it was so successful that I've been grading papers for a week and a half.
Wow, that's awesome. That is great.
Yep.
Good practice for you.
So do what?
Yeah, I didn't think I would be involved in virtual learning, but they put our July class up on the council website, and we had 50 students in 4 hours.
Wow. That's great.
So for people who don't know how to use this stuff, down at the bottom of your Zoom screen is a chat button. If you click that, you get a chat window on the right, which is just chatting between everyone that doesn't get seen, or you don't hear anything. And you can see, if you get there, that you can message a single person, or if you're just making a comment, you can send to everyone. So we can chat back and forth over here even whilst the speaker is speaking.
All right, guys, I'm gonna mute everybody now and we're gonna get started.
Great.
All right.
Go for it.
Oh, okay, so am I on the air now? I guess I'm on the air now, okay. Well, this is the
You're there.
This is the first virtual meeting for the LA Astronomical Society. YouTube and search LA astronomy. Okay, there's a 12-second lag on the YouTube, and it's a broadcast only, no chat feature on the YouTube. Okay, we'll get directly into the announcements because we're not going to do a lot of back and forth if we can avoid that. First announcement that we need to discuss, we've been discussing this at the Board of Directors meeting, is Lou Chilton and Carla Chilton has been nominated for a life membership for the LA Astronomical Society, and I think also for a life membership at the Lockwood Valley Star membership. So just wanted to put that out there tonight. And next month at this time, when we have the meeting, we will be voting to get a show of hands or voting to approve Lou Chilton. That has to be done by the general membership. We have to have at least 30 days prior before we vote on the motion for Lou Chilton become a life member. Okay. Also, Lockwood Valley is open for dark sky night and family nights, and we adhere to the social distancing and face masks required. Sign-up sheet and COVID question and agreement to adhere to the rules, and the link it will be available in a few days on the LAS website. I think Andy will be sending that out. We will also be opening Ford Observatory up this weekend, although we will be doing a maintenance up at Ford Observatory during the day on Saturday. I think Joe and Greg Thomas will be doing a maintenance on the dome at Ford Observatory. Okay, Mount Wilson, Griffith Park. The Mount Wilson and Griffith Park Observatory star parties are still canceled. They will be canceled until Griffith Park and Mount Wilson is open to the public again. Also, Garvey Ranch is still closed until the city of Monterey Park gets a clearance to open up Garvey Ranch. Garvey Ranch is still closed. Although we did have senior moment here. We had Vance Tyree go in and get the computers out of the observatory so they wouldn't be damaged by sitting in the observatory. So he was able to go in and get those computers out. Okay, now we're going to be doing, we also have been doing our board meetings via Zoom for the last, since I think the April meeting was the first meeting we did via Zoom. So we've been doing the board meetings via Zoom also. So, and then you can also email Spencer Soho for the link for the Zoom meetings. And his email is secretary@laas.org. And as we mentioned before, we will resume the door prizes at the next meeting. We're going to be trying to have Amazon gift cards and pitch for online smiles. So hopefully that works. I think that'll work out. Greg Thompson is working on that. Now I can't do what we normally do, ask for any new members or ask for any guests, because we're not going to show up hands to be able to do that. So it's kind of a little different situation this time around. And hopefully everybody heard me on everything I mentioned. And now I'm going to turn over the next part of this meeting over to Greg Thompson, because he's going to give you the information on the scouting outreach. And he's also going to talk a little bit about Comet Neowise. It was kind of spectacular that comet happened to come around when it did, because I think we all needed a shot in the arm in astronomy, and I think that helped us out. So Spencer, why don't you go ahead and turn us over to Greg Thompson, please, if you can.
Okay, before we do that, just
Yes.
one other announcement. The Lockwood Committee meeting is meeting on Wednesday at 8 p.m. And so Andy's already sent out a link for the Zoom meeting. Okay.
Okay, so now Greg Thompson.
Right. Okay, Greg, go ahead.
Okay, thank you a lot. I just wanted to update the membership. The Scouting Merit Badge Program, the Astronomy Merit Badge Program, we had expanded it to 3 classes from 2 classes last year. It was very successful last year at Garvey Ranch, but at the last minute, we reconverted it into a virtual program, and a fair amount of effort went into that, and club members helped. The club has sponsored the Zoom account that we're using here, and Spencer and I and others on the board have been learning how to do the Zoom sync. And the scouting program was also hosted by that same platform. So thank you to the club for supporting our scouting program. As virtual students, we've had so far 3 sessions. One of them, we had so many sign up that we had to do a second one. So right now we've had about 60 scouts earn the badge. And just to share with membership, the Astronomy Merit Badge is not just listening to Greg Thompson talk for half an hour. These scouts have to fill out a 25-page workbook that includes bullets on optics, spectrography, stellar evolution. They have to do independent observations, including mapping and drawing the moon for 4 nights and the rotation of the Big Dipper 4 different times during a session in 1 night. We also included in our virtual program, to make it more fun with the scouts, live demos using the Zoom platform to its best ability. And probably the part that the scouts have loved the most is the live viewing, where we actually go to a member. In this case, Spencer gets a lot of credit for helping us work that out, but we're able to go live to his astrophotography rig and show the scouts stuff live and in person, and they can ask questions and we can move around, and we've gotten a lot of positive feedback on that. The career panel at the end, Tim has really helped us with that. He's got 50 scouts now that all want to be astrophysicists because they think it's going to be so cool. And so Kevin Gilchrist helped out with some really beautiful photos he had taken, just sharing them and answering questions. So that's been very successful. We have 1 more class next week, next Wednesday night, and I will keep grading workbooks. We're talking with council, when things open back up, things we can do next year. But right now, this is like our main outreach program. And we've been getting super positive feedback, both from the parents and from the scouts themselves. I got an email from a parent just 2 nights ago where her 14-year-old son had spent his birthday money on a new telescope instead of a new Xbox, and wanted a few tips on how to set it up. And then I got one back and said he was able to see Saturn and he was thrilled. So if one young man, 14 years old, got his first telescope because of our program and the support of the club, I think that's a huge success for our hobby. So I just want to thank everyone. We'll continue the program. If you would like to participate or help in any way with viewing or sharing or with the career panel, the last session is not this coming Wednesday, but the following Wednesday. Please email me through the club contact or the boards or chat in there, and I can send you my email address. We're happy to have the help. Successful program. Thanks a lot from the support from the club. So that's kind of the summary. If you have any questions, you just go ahead and type them in the chat, and I'll type back as I'm taking notes here. I just asked Curtis to throw the comment on our agenda, just to kind of as a group acknowledge that we had this amazing event. And I followed it a lot through our groups IO, the boards that a lot of you use. And I want to thank everyone for posting really, really amazing photos and times and information that I used in my own observing to go out and see the comet. I accepted an invitation to the small group that went up to Ford Observatory about 2 weeks, and we set up with some lawn chairs and telescopes out behind the dome and just had an absolutely beautiful view of it. And it was a really, really fun night for me to see the comet. On our July 22nd class, about half the scouts were able to go out with binoculars and see the comet during our break, which was pretty cool. I don't think they were expecting that treat. And then as a result of that, I got about 20 emails from scoutmasters all across the LA basin on how do I help my scouts find the comet. So that connection worked really well. Thanks, guys. I saw some of our astrophotographers post these beautiful pictures, and I got to go up to Ford and actually see what it was like in my own scope, and that was really fun. I highly recommend, if you haven't used our boards, our Groups IO, to see what some of these astrophotographers in our club can do and the information they exchange. I learned a great deal, both about observing comets and some of the astrophotography stuff. I'm just getting started on that myself, and I've got plenty to learn. But so I just wanted to acknowledge that we had this amazing comet. It's actually been a while since we had a comet that was, visible to the naked eye with a long, beautiful tail like that. And it was really cool. So if you have any questions immediately, feel free to type them in the chat, and Spencer and I will read them back. Anyway, that's my two topics, Curtis. I think people can type in the chat if they have questions, and I can go back on mute.
Oh, okay, we can go ahead. I think it's time for our speaker. And I'll let Spencer take over and introduce our speaker for us for tonight. It should be a good talk. So
Sure.
Spencer, have at it. It's all yours.
Thank you. Well, thank you, Dr. Fuller, for agreeing to speak for us. Dr. Fuller is an assistant professor of astronomy at the Caltech. He got his BA from Whitman College and an MS and PhD in astronomy and space sciences from Cornell University. He's held positions as a NASA Earth and Space Science Fellow at Cornell, a KITP postdoctoral scholar at Cavalli University Institute for Theoretical Physics. He's a DuPont or DuBridge postdoc fellow at Caltech. His research interests are in theoretical astrophysics, especially stellar and planetary systems, with a focus on wave propagation within stars and planets as they relate to binary stellar evolution. That's a mouthful. So in his words, most of my research focuses on the physics of vibrating spheres, fluid spheres. There has applications within astronomy. So as a graduate student, he studied tidal interactions in merging white dwarf systems, heartbeat stars, and more recently studied magnetic fields inside of red giants, the deep interior of Saturn as revealed by its rings, and long-term evolution of Saturn's moons. So I'm going to turn this over to Dr. Fuller, who's going to speak. His title is Sounds of the Stars, Journey to the Center of a Star.
Okay, thank you, Spencer. And thank you for inviting me. It's really a pleasure to be talking to you all tonight. Although it'd be great if we were actually at Griffith, that would be wonderful, but we'll just have to let our imaginations do the work tonight. Although I will give you some nice images and some sounds to help you understand some of the things I'm going to talk about. For those of you, sorry, just a second, let me switch screens. For those of you listening on a laptop, if you can find some headphones, that will actually work a lot better for this talk. I'm going to play a lot of sounds that don't always come through very well on chintzy laptop speakers. So yeah, if you find some bigger speakers or headphones, that might work a little bit better. Okay, does everybody see my screen? All right. Yeah, so I'm Jim. I'm a professor of astrophysics at Caltech, and yeah, I study a lot of things, but one of those things is astroseismology, which is essentially the way of figuring out what's deep inside of a star, what's at the center of a star, based on the way that that star pulsates. So essentially the sound that the star makes. So this is similar to Earth seismology, where you try to figure out what's inside of the Earth based on the way the Earth shakes. And it's just the same idea applied to stars. So tonight we're going to take a journey to the center of a star. We're going to listen to some sweet stellar beats, and we're going to dabble in a little bit of theoretical astrophysics. So here we go. Okay, so if you could see a pulsating star, it might look something like this. The colors here might indicate the surface temperature of the star. Stars are not just static spherical objects. They actually pulsate. Almost every star pulsates at some level, including the sun. These pulsations are composed of waves, mostly sound waves that travel through the star, so into its interior and then back out of the surface. And that creates a specific pattern at the surface. So if we could hear that sound in the star, you'd hear something like the background music that you hear there. Now, of course, we can't actually hear stars because sound does not travel through space, so we have to be a little more clever. In fact, we can't even resolve the surface of a star. Most stars are so far away, they just look like point sources. So what we actually do is we just measure their brightness. So there's a few satellites up there, like NASA's Kepler and NASA's TESS satellite, that are really good at this. They just measure the brightnesses of many different stars as a function of time. And so if you had a star pulsating at a single frequency, you'd see a brightness, a sinusoidal brightness fluctuation as a function of time. And it's that frequency of the pulsation that really tells us a lot about the star. That frequency you can think of as a musical note. And a star plays a set of musical notes. Sounds like we have a very enthusiastic young astronomer there. So a star plays a series of notes. Those notes, like a musical instrument, tell us something about the stellar structure. So to understand how this tells us about a star, I have some videos for you. So basically, the basic idea is that little things tend to make high frequency sounds and big things tend to make low frequency sounds. So a little star might make a sound like this, like this. All right, so that would be like a cute little star making its sound, and a really big star might make a sound more like this. This is an octobase, and because the instrument is so big, it takes sound waves a long time to travel across the strings, so it makes a very low frequency sound. It's the same idea with stars. Really big stars take the sound waves a long time to travel through it, so they typically make very low frequency sounds. So let's compare pop stars to actual stars. So in terms of the frequency of the notes that they sing, pop stars usually sing at about 1,000 hertz. So the human voice is a few hundred or a few thousand hertz. Whereas stars span a much wider range of frequencies, anywhere from 10 to the minus 7 hertz or so, all the way up to about 1,000 hertz. So the highest frequency stars do actually play sounds roughly in the human hearing range, but most of them are much lower frequency. Our own sun pulsates primarily at periods of about 5 minutes. So that would be a note that's far too low for us to hear, but that's pretty typical for stars. Now, typical stars usually only play notes of, maybe in 1 or 2 octaves. So they don't quite have the vocal range that a talented pop star like Mariah Carey has. But altogether, a stellar chorus would have an extremely wide range. So the different notes they play really tell us about all the different kinds of stars that we have out there. So here's a couple of real star sounds. So to make these star sounds, what we've done is just measured the brightnesses of a few stars. And then you basically just turn that waveform into a sound wave, and then your speakers will play that sound wave. Now, to get it into the human hearing range, these have been sped up by about a factor of 1,000,000. But the notes and the different notes that they play are roughly correct. So this is what a star like the sun would sound like. Okay, so just like people, not every star has a great voice, but they all have different voices that we can use to recognize them and learn about their properties. Here's a slightly bigger star. The first star was like the sun. This is the sound of a subgiant star, slightly bigger than the sun. That means it's slightly lower frequency. Then if you go to an even bigger star like a red giant star, you can hear an even lower frequency song like this. And that one, the notes are so low that on my laptop speakers, I can barely hear them. But with a good pair of speakers, you can hear that. So let's talk about how we actually use this information to learn about a star. So like I said, stars pulsate, but they don't usually pulsate in just one note. They pulsate in many notes at a time. So we could think of that as each star having a different timbre to its voice. So as an example, this would be a plot of, say, brightness as a function of time for a star that pulsates in 2 different frequencies at the same time. So you can see there's this slower term modulation here that produces the low frequency note in this brightness versus frequency domain. So this is essentially a Fourier transform of the signal on the left. And then you can see this shorter term oscillation here. This has a higher frequency, and that produces this higher frequency note there. So stars just like this pulsate actually typically in 10s or 20 different notes at the same time, sometimes dozens of pulsations at the same time. So the actual data for a star can look kind of complex. So this is actual data taken by the Kepler satellite for a red giant star. And what's plotted here is just the measured brightness of the star as a function of time. So the great thing about Kepler was that it made measurements of stars every 30 minutes for most stars, and it just did that continuously for 4 years. So we have this beautiful data, and it may not look so beautiful, but when you take a Fourier transform of data like this, you see all the notes that the star plays. So that's what's shown here. This is a Fourier transform of a signal like that, where now you see lots of very organized structure. So each one of the peaks in this diagram corresponds to a different note that this star plays. So this star plays about 20 different notes here that we can detect. And these all are essentially one pulsation, different way that the star pulsates. So each of these corresponds to essentially a different shape that the star makes, which I'll talk about in a minute. These peaks labeled with a 0, those are called radial oscillations. So that's when the whole surface of the star actually expands and contracts coherently. Whereas the peaks labeled 1, those are called dipole oscillations. And what's happening there is the surface of the star is actually moving back and forth. And different layers of the star inside of the star moving in opposition. So you have different layers of the star basically moving back and forth relative to each other. And then these peaks labeled 2, those are called quadrupole oscillations. And that's basically the whole star squishing back and forth into a football shape and then back into a sphere and into a rugby ball shape back. So these are all different manners in which a star can pulsate. But this pattern of peaks we see tells us a lot. So the first thing you'll notice is this whole power spectrum is centered around one note that has the highest amplitude, and we call that the frequency of maximum power. So in this case, it would be this note right here. And it turns out that that note is determined by the surface gravity of the star. for most stars like the sun, these pulsations are excited by convection at the surface of the star. And the characteristic frequency of motion of that convection is determined by the surface gravity of the star. So it turns out if we measure this frequency of maximum power, we actually get a measurement of the surface gravity of the star. The other thing you'll notice is there's this very organized pattern where you see this quadrupole mode and this radial mode right next to each other. And then you see a dipole mode, and then you see that pattern repeat, and it repeats several times here. So we can measure this frequency spacing between successive overtones of that pattern. And that's called the large frequency spacing. And it turns out that that frequency is determined by the time it takes a sound wave to travel to the center of the star and back out. So if we measure that frequency separation, like we can do here, we can measure the time it takes sound to travel through a star. And it turns out that that is directly related to the density of the star. It goes as the square root of the density of the star. So if we measure the surface gravity and the density of the star, we can then solve for the mass and the radius of the star. So we can actually figure out how massive a star is and what its radius is, how big it is. And this is information that we couldn't get otherwise because stars are just points of light, and we have no way for most of them of measuring their mass or radius. But we can do it through this technique. So this has been one of the big breakthroughs of astroseismology. So we can actually do a lot more than that. That kind of tells us about the bulk properties of the star. We'd also like to know a little bit about the details of what's inside of a star. So like I said, astroseismology is somewhat similar to Earth seismology, where in Earth seismology, you have an earthquake. Let me pause this movie. You have an earthquake that launches sound waves that travel through the Earth. And then you have seismographs on the surface of the Earth that record those sound waves. And the Earth has two kinds of waves that can propagate through it. There's P waves, which are these red arrows, and there's S waves, also known as shear waves, that are the blue arrows. So in stars, we don't have S waves. The reason is those are shear waves. Those only propagate through a solid medium. And that's how we know the Earth has a liquid core, is basically we can see that those S waves can't travel through the liquid core. There's a shadow of the core because the S waves can't travel through. So we don't have those waves in stars, but we do have these red P waves here. So if you looked at the path that a pressure wave took, a P wave, as it traveled through a star like the sun, it would take a path something like this. So basically it propagates in towards the interior, but then it gets refracted and propagates back out to the surface where it reflects, and then propagates back into the interior again. And so the given sound wave will propagate, it'll bounce back and forth many times before it damps out. So it'll trace out a pattern something like this. So we don't actually see this pattern, but this is what an individual sound wave would do as it propagates through the sun. So what we actually see again are these power spectra. So on the top panel here, this is a power spectrum of a star quite similar to the sun that pulsates at periods of about 5 minutes. And this is a pretty organized power spectrum that we know how to interpret. If you look at a red giant star, so a star like the sun, but that has evolved for another 5 billion years and swelled up into a big, very bright red giant star, then the power spectrum gets much more complicated. So again, this is real data for red giant star. And this looks like a mess, but we've actually learned how to interpret all the different peaks in these power spectra pretty well. So actually, a lot of the features are the same. So you see here, there's this big L equals 0 mode next to an L equal 2 mode. And you see the same kind of pattern in a star like the sun. So those are very similar. What is quite different is you'll notice the L equal 1 modes, which in a star like the sun are just one peak. In a star like the red giant, they have an enormous amount of structure to them. You actually see many different L equal 1 modes. And the reason for that is that the structures of red giants are different. And that means the waves propagate in different ways, and there's basically many more ways in which a red giant can pulsate as a result. So if you watched a wave propagate through a red giant, it would take a path something like this. So again, it propagates into the center, but in this case, the pressure wave at the surface can convert into a different kind of wave in the center of the star. This is called a gravity wave or a buoyancy wave. So it's a wave that's essentially restored by buoyancy forces instead of pressure forces. And those waves, it turns out, can propagate all the way to the center of a red giant star. So when we look at the power spectrum of a red giant star, we're getting information about the very central layers of that star, which is something actually we can't do for the sun, even though it's much closer. So we get really exquisite information about the very central regions of these red giant stars. Yeah, so this movie is pretty mesmerizing. I could let this play all night. But the reason the red giant power spectrum is so complex is that this extra propagation cavity in the center gives us a lot of different oscillation modes of the star. So you see these L=1 modes are split into groups. So you see that each one of these groups here actually has 3 components to it. They're triplets. I will come back to why they're triplets. But you can see here that these groups of modes are spaced by some characteristic frequency. So basically the frequency difference between these blue shaded groups and these red shaded groups is a characteristic value that we can measure pretty well. We've measured that for thousands of red giant stars now. And when you put those red giant stars on a diagram, you see a lot of interesting structure. So what I'm showing here is a plot that shows on the y-axis, it shows this frequency spacing between those different groups of L=1 modes. And then on the x-axis is that frequency spacing between the radial oscillation modes here. So remember, that tells us about the density of the star. And the y-axis, it turns out, tells us about the core structure of the star. So you see there's 2 very clear different populations of stars. There's this big long branch here. And it turns out these are all red giant stars that are burning hydrogen in a shell around a helium core. So they've fused all the hydrogen in their centers into helium. There's no more hydrogen left in the center. So all the power from the star is coming from hydrogen just outside of the center that is now being fused into helium. And as stars burn that hydrogen, they swell up into red giants. And so as we move from the upper right to the lower left here, we're seeing stars that are becoming larger and larger as they're burning hydrogen in a shell around their core. Now you also see this totally different group of stars here. These are stars that have built up enough helium that the temperature is hot enough and the densities are large enough at the center of the star that the helium starts fusing into carbon and oxygen. So this will happen to our own sun in about 5 or 6 billion years. It will start burning helium into carbon and oxygen at its center. And that changes the structure of the core of the star. So it turns out it increases this period spacing here. And so we get the separate group of stars that are all burning helium into carbon. So if I looked at one of these stars at the surface and one of these stars, they would look almost identical. They're almost the same brightness and the same temperature. But their internal structure is much different. And that tells us the evolutionary state. And that, again, is something we had never been able to figure out before. We didn't have any way of distinguishing between those 2 different types of stars, but now we can do it by listening to the sounds that stars make. So remember I said that those groups of modes, they're split into triplets, into 3 different components here. And the reason for that is that stars rotate. So because a star rotates, you have, it turns out that these dipole oscillation modes, some of them basically bounce up and down along the rotation axis, okay? But some of them propagate in the same direction as the star is rotating. And so that means they get Doppler shifted to higher frequencies. So just like a car coming down the highway makes a sound that goes from high pitch to low pitch, it goes, right? That's just the Doppler shift of the car's sound. When it's moving towards you, it gets shifted to higher frequency. When it's moving away from you, it gets shifted to lower frequency. So this slightly higher frequency peak here, this is a mode that's rotating in the same direction as the star is spinning. And this is a mode that's propagating through the star in the opposite direction. So by measuring this frequency splitting between these triplets, we can measure the rotation rate of the star. And not just the surface rotation rate, we can actually measure the rotation rate of the inside of the star, which is really neat. So stars don't rotate like rigid bodies like the Earth does because they're not solid. They're made of gas and plasma. And it turns out their interiors rotate faster than their surfaces. And you can see that here. If you look at this triplet, you can see that the frequency spacing here is larger than it is for this group. And the reason is this is an oscillation of the star that's mostly confined to the interior of the star, which rotates faster. And this is an oscillation that's mostly confined to the exterior of the star, which rotates slower. So we've been able to measure the internal rotation rates of many stars that way. And we've learned all sorts of interesting physics that way. So another thing that we can measure, and this is something I've worked on, is we can measure magnetic fields inside of stars, which again is something we could never do before. And the reason is basically, essentially a magnetic field acts like a big dampener inside of the star. So it's like if the star was a trombone and you just stuffed a bunch of rags into the trombone, the sound it would make would get suppressed. And so that's what happens to these red giants that have magnetic fields inside of them. So this is a normal red giant that doesn't have magnetic fields. And you can see there's these red peaks. These are those dipole oscillation modes. They have high amplitudes here in this star. This is a star that looks almost identical, but now you can see those red peaks have been suppressed, whereas it still has the big radial oscillation modes here. So it turns out this star is a star that has a strong magnetic field at its center, and that selectively suppresses these red oscillations, which are the ones that propagate into the center of the star and back out. So we've been able to learn all kinds of interesting things that we never thought we'd ever be able to see. Okay, so I'm going to move on to binary stars next, but are there any questions about these single stars?
Yes, I have a question.
Okay.
When you described how the waves go through a star,
Sorry, I missed your question because you got muted.
okay, there we go. I don't know why. All right. So when you were discussing the oscillations of the pressure waves of a star the size of our sun, you were showing how it's reflected back and forth around the exterior, and the core, nothing goes through that core, I think, right?
Yeah, so there are some oscillations of the sun that go very close to the core. Actually, some of the radial oscillations essentially go all the way through.
Okay.
So we do get a little bit of information about the core, but it turns out that we don't get very much because at the center of the star, the sound speed is very high because the temperature is very high. So the waves just pass through that part of the star really quickly. And that means that we actually get very little information about that part of the star.
Okay. Now, okay, you were talking, all right. So then comparing that to a red giant, in the red giant, in the center cavity, you were showing how there's these oscillations that just swirl and go and way, a lot more complicated. And I don't understand why that is, because, okay, there's more in a red giant. It's hotter in the center, right?
Yep.
And it would be denser in the center, wouldn't it?
Yep.
Okay.
This is a great question. Your intuition is fantastic, but I have omitted some of the physics.
Okay.
So it turns out that you need to do some math and some physics to figure out exactly how a wave of a given frequency will propagate through a medium. And it turns out that there's two characteristic frequencies inside of the star. One is like a sound speed crossing frequency, and the other is a buoyancy frequency. It turns out in the sun, the waves we see are in the high frequency limit of essentially being sound waves. But in the center of a red giant, because the frequencies are lower, and like you said, the temperatures at the center are higher, it means that the waves at the center of those stars are actually in a low frequency limit where they behave like a different kind of wave called a gravity wave. And it turns out that those waves actually propagate much slower than sound waves, which is a little surprising.
Okay.
But they move in the radial direction much slower. And so that's why the path that the waves take turns into a spiral instead of an almost radial motion.
Okay, thank you.
Yeah.
Are the gravity waves directly detectable at the surface?
Not in the sun. And in red giants, they're not directly detectable because where the wave propagates as a gravity wave is deep inside of the star.
Yeah.
And so we see modes that are actually mixed. They're sound waves at the surface, but they're gravity waves in the interior. There are some other kinds of stars, so stars that are about twice the mass of the sun. It turns out that those stars, there are gravity waves that propagate all the way up to the surface of the star. So in some other stars, we see gravity waves right at the surface.
Okay.
But remember, these are buoyancy waves. They have nothing to do with gravitational waves that are an outcome of general relativity.
Yeah.
Okay, any other questions before I move on? All right. So I'll talk about some binary stars as well. So lots of stars are binary stars. About half of stars are binary stars. And those binary stars can gravitationally interact with each other, and that can make them pulsate and sing a new kind of song. These are stellar duets. And I've studied a class of stars called heartbeat stars that are especially interesting example of a stellar duet. And what these are two stars that orbit each other in a very eccentric orbit. So I'm going to play a little movie. In the top panel, you see two pulsating stars, and their orbit is eccentric, so they pass very close to each other at their closest approach. That's what their orbital motion would look like. And in some of these stars, they pass just within a few stellar radii of each other at the closest approach. So that means they actually get tidally distorted. They change their shape due to the gravity of the other star. So this changes the brightness of the star right when they have their closest approach. But it also essentially, it rings the whole star like a bell. It gets deformed right at periastron, and just like a bell, if you punch a bell, it doesn't just stop as soon as your fist leaves the surface of the bell. It keeps oscillating. And so stars will do this as well. So they oscillate all throughout their orbit in many cases. So that's what's shown here. On the bottom is data for a star called KOI 54, which oscillates. It's two stars that orbit each other every 45 days. Then they oscillate throughout the orbit as well. So if you actually listen to the sound that a system like this would make, again, it's been sped up to put it into the human hearing range, but it would make a very interesting sound like this. Okay, so there's two components there. There's a high frequency pitch that's due to these oscillations throughout the orbit. But then there's also a beat. I don't know if you can hear that beat. That beat is basically due to when the stars pass by each other, you get this extra impulse that produces the beat sound that you're hearing. So again, by studying those sounds, essentially, we can learn about these binary stars. This is another one. This is real data for one of those binary stars. This one pulsates. So it turns out that these pulsations, they're exact integer multiples of the orbital frequency. So in this case, I think this pulsation is 23 times the orbital frequency, exactly. Then you see this extra distortion here when the stars get very close to each other in their orbit. So this one has a slightly different sound. So again, it's a tone and a beat. In this case, the tone's a little bit lower frequency compared to the beat, but it's the same idea. This is yet another one. Here I'm only showing part of the orbit. It turns out that this one oscillates, one of the stars oscillates exactly 221 times every orbit. And so in this case, we basically only hear that tone. We don't hear the beat so much. I've written a whole paper on that star, which I can tell you about some other time. This is a different star where you might want to cover your ears for this one. This one is not too harmonious. So in that case, there's two main frequencies. There's this frequency, and then there's the longer term orbital frequency. So there's two notes at I think it's a 6-to-1 ratio in that case. And to our ears, that sounds pretty bad. But it is an exact integer multiple because of the physics that excites those oscillations. Basically, the stars force each other to oscillate at exactly some integer multiple of the orbital frequency such that the oscillation's at the same phase every time the star comes back through its orbit. So it gets even more complicated. In some of these stars, they orbit so close to each other that they're continuously tidally distorted. And so just like if you took a musical instrument and bent it into a different shape, the sound it would make would change, the pulsations change. So they can exhibit a different pattern through the star. So this is an animation of a star I made where we can basically see this process going on. What happens is the pulsations, they end up lining up with the axis that connects the two stars that are in orbit with each other. And in this case, the pulsation pattern propagates around that axis connecting the stars. So you get this very intricate pattern that changes as the stars orbit each other. So we can measure that changing brightness. And in this case, when you sonify that, it makes a sound like this. So this one doesn't come through very well on laptop speakers. But what you'll hear is you'll hear kind of a pulse that's going in and out. And that's because, well, you can see in the bottom right, this is the light curve of the star like this. Basically, you have some sound wave, which at some phases of the orbit, it's a very large amplitude. That would correspond to basically when we're seeing the star edge on like this. And at other phases of the orbit, the sound wave, the brightness fluctuation that we measure actually has very small amplitude, like at this orbital phase. And in this case, it's because part of the star is hot and part of the star is cold, and those patterns cancel each other out. So we measure no brightness fluctuation. So yeah, it can get very complicated. I'm almost through, but I should mention that it's not just duets, there's also stellar trios and stellar quartets. So if you have 3 stars orbiting each other, you can get more intricate motion. So this is an animation of a star system that I've studied called the Trinity star system. And this contains a red giant star that's orbited by a pair of sun-like stars. And those sun-like stars orbit each other roughly once per day. So if you watched the system evolve in time, all the stars would orbit each other like this. And it turns out that the orbital motion of these sun-like stars, that actually causes the gravitational field to fluctuate. And that excites sound waves inside of this red giant star. And that causes the red giant star to pulsate. And we can actually measure that with the Kepler satellite. That one makes an interesting sound. I haven't sonified that one. And there can also be these quartets. This is an example of the power spectrum of a system that's basically 2 of those heartbeat stars, but those heartbeat stars then orbit each other. So you have 4 stars all orbiting each other in these very complicated patterns. And that makes a very complicated power spectrum like this. But again, we can learn that this is a quadruple star system just by measuring their brightnesses of the stars. So I'm almost done. The last thing I will mention is that we can do a lot of this for planets as well. So I said, you know, a lot of astroseismology is actually built on the physics of Earth seismology. And we'd love to do it for other planets, which, you know, are a lot closer than stars, so we should be able to do it. But it's actually quite difficult for a lot of the planets in our solar system, like the gas giants like Saturn, because they do not have solid surfaces, right? So how would you put a seismograph on a planet like Saturn? It would be pretty tough. So it turns out that we can actually measure pulsations of Saturn using its rings. So Saturn's rings essentially act like a big record player that record and amplify the pulsations of Saturn. And the reason for that is that Saturn pulsates at very small amplitude. It turns out the motions of particles are just about 1 meter, and it pulsates once every few hours. So the motions are so slow we could never measure them directly. But that actually distorts Saturn's gravitational field just a little bit. And it turns out those distortions of its gravitational field actually create spiral density waves inside of its rings. And we can see those waves in the rings. And we can measure the frequencies of the waves in the rings. And that means we can measure the frequencies at which Saturn pulsates. So this has allowed us to learn new, very interesting properties of Saturn's internal structure, which actually we understand very poorly. But now that we've been able to do a little bit of seismology on Saturn, we've learned quite a bit about its core structure. And I'm actually working on that with a postdoc here. We're writing up a paper about what's at the center of Saturn. So how big is its core based on the pulsations that we see in its rings. So we've learned that Saturn has a core mass of something like 20 Earth masses based on the patterns in its rings. So that's pretty cool stuff. So I'll leave you tonight with a stellar symphony. This is an orchestra put together by combining many of these stellar sounds into one big orchestra. So I'll let this play, and then afterwards I'll take more questions. Okay, thank you, everybody. I can take more questions now.
I have a question.
I encourage those of you who don't have headphones on right now, go back and look at the YouTube recording of this and put on some headphones, and I think you'll find that those videos sound a lot better. Okay, go ahead.
I had a question on some of the last graphs that you showed us. We were looking at a lot of the peaks. It seemed like that there was an awful lot of data down at the bottom, even further back when on the other ones, more back.
Which? Oh.
Yeah, I think what was it, one more back?
This one?
Yes. So we were talking a lot about all of the high peaks, but there's so much data down below. What is the smaller peaks in
all of
the
these?
lower range? What is that indicating? Is that giving you information, or is that just static?
Yeah, so I think it's a combination. At the very bottom here, this is just noise, I think.
Okay.
But there are a lot of oscillations that we can just barely detect. So for instance, some of these oscillations are probably real ones that are just barely sticking up above the noise.
They don't seem to be in much of a pattern of any kind either.
Well, I think there is a
Small
pattern.
ones.
The problem is that the amplitudes are not always, the amplitudes fluctuate a little bit. So you can have, as an example, if you look at this triplet, this mode has a slightly higher amplitude than this mode. And that's probably those amplitudes just fluctuate a little bit kind of randomly because they're excited in a random fashion. So that can happen for these modes too. So some of them are buried in the noise and some of them stick up above them.
Okay, thank you.
Yeah.
Really nice talk, by the way. Thank you.
Thank you.
I have a question. Are you able to hear me?
Yep.
Hi, this is David. How does the astronomical, I guess everybody involved with planets and everybody that does what you do, how does this help us to? I mean, where does this take us to? What's the next step of learning about this? I guess it's fascinating to me because I have a musical background, of course, as some of you know. And how you're explaining it with the musical instruments and tones is fascinating. So where does this lead us to? I'm just curious.
I mean, I think where it leads us to is understanding what's inside of stars and what are the physical processes that are occurring. So, like I said,
beyond all this, where does this take us to?
Well, I think that's more of a general question about astrophysics research.
Okay.
I mean, a lot of it it's the modern day equivalent of exploration. This is the best way to explore new parts of the universe that, we can't travel there. We don't have the technology yet, but we can see those parts of the universe, and so we can still explore them.
Very impressed with what you do. I got to tell you, I'm just totally blown away. This is fantastic. Thank you so much.
I'm interested in the differences that might be in contact binaries as opposed to non-contact binaries. Have you looked at the contact binaries? Are they different in terms of what they show?
Yeah, that's a good question. So for those of you who don't know, contact binaries are essentially binary stars that are transferring mass to each other. And so they, instead of looking like two different stars, they're basically one peanut-shaped star that orbits itself. So these stars here that I showed you that are very heavily tidally distorted, some of these are actually probably contact binaries or almost contact binaries. So that's an example where, because of the tidal distortion, it does change the way that the star pulsates. And what's most important is the pulsation becomes aligned with the binary axis rather than with the spin axis. So that actually causes the pattern to be modulated over the course of the orbit, which is not true for normal or single stars. That's a big difference between contact binaries and other stars.
Thank you.
I had a couple of questions in the chat area about, do we get any good data from Juno about Jupiter and its core and so forth? And do planets affect the stellar observations enough to actually change the geometry of the star?
Yeah, those are two great questions. So there is some hope of detecting oscillations of Jupiter with Juno, which is the satellite orbiting Jupiter right now. So what Juno does is it measures its position with GPS or with radio tracking very precisely. And so that means it can measure Jupiter's gravitational field very precisely, because the gravitational field changes the orbit of the satellite, and that's what the satellite can measure. So there is some hope that if Jupiter is pulsating, it will essentially cause slight deviations in the orbit of Juno that we can measure. There are efforts to do this. I don't think that we will be able to get the same kind of information that we get from Saturn's rings, but we might at least be able to see if Jupiter is pulsating or not. And then with a future mission, we might be able to do more, to make better measurements and actually learn about Jupiter's core. And then you asked about planets exciting oscillations and stars. So I actually have a student this summer looking for oscillations of stars excited by planets. So there are some exoplanets that orbit in very eccentric orbits, very close to their host stars. And so we're looking for pulsations of the stars excited by the planets. The problem is that planets compared to stars are very low mass, and so their gravitational forces are much smaller, and so the amplitudes of pulsations that they excite will be much smaller. So we haven't found anything yet, but we're looking, and I think eventually we will get to that point where we can detect oscillations of stars excited by planets.
Does the sampling rate affect what kind of frequency you're able to detect, and how could you get 1,000 hertz?
Yeah, great question. So with the Kepler satellite, we cannot get 1,000 hertz. That makes a measurement every 30 minutes, or the TESS satellite makes a measurement roughly every 2 minutes. Yeah, so you can't get to 1,000 hertz with that. The stars that pulsate at about 1,000 hertz are neutron stars. So those are stars that have about the mass of the sun, but they have the size of a city, basically. They're incredibly dense, and that's why they can pulsate so fast. Now, usually we don't actually see pulsations of those stars. We see them rotating, and some of those rotate close to 1,000 times a second. So what we actually see is we see those stars emit radio waves, and the radio waves are modulated at that spin frequency, because sometimes they're directed at us and sometimes they're directed away from us. So those are called pulsars. So to do that, we need to make different kinds of measurements, and those are done with radio telescopes, and those can record data much faster. So they can make pulsations at a higher frequency.
You said that normal red giants don't have magnetic fields.
Mm-hmm.
They don't?
Well, they don't have.
Makes...
That's a great question. They don't have strong magnetic fields. It's probably the better way of saying it. So let me find that picture. We don't actually understand this very well, but what we think is that most red giants do not have a strong enough magnetic field to affect their pulsations very much. And that produces a power spectrum like this. It turns out about 20% of red giants have a power spectrum like this that we believe is caused by strong magnetic fields. And we still don't really understand why it's only about 20% of red giants. It turns out that it's slightly more massive red giants that show this pattern, but it's still only about half of those ones. So we don't understand why some have magnetic fields and some don't. That's something I'm trying to figure out.
Okay, thank you.
Would it be possible to use radar to observe Venus, looking at the Doppler shifts to see pulsations on Venus?
Good question. I think in principle, yes. So you're thinking about, you bounce radar off of Venus, and because Venus is shaking, you can measure the motion of its surface. I mean, if Venus pulsates similar to the Earth, then you'll know that that pulsation amplitude is very low and very infrequent, right? Earthquakes are not always going off under our feet. So the motion of the Earth's surface is, for the most part, is very small. And probably it's the same for Venus. And I think Venus is actually thought to be less tectonically active than the Earth. So in principle, we could do that, but I think in practice, the signal would be extremely small. I think you'd have to land something at the surface of Venus, which has been done, but the surface is so hot that most satellites melt pretty quickly at the surface. So.
And waves in the atmosphere couldn't be detected that way?
Maybe it could. I know that some earthquakes on Earth have been detected because they generate waves which propagate up into the atmosphere. I don't think that would make much of a radar signal because radar penetrates the atmosphere, at least at most frequencies. Maybe there's some way of detecting it, or if you had, I know there are ideas to have satellites that essentially float around in Venus's atmosphere. They're like a balloon that floats around in Venus's atmosphere. So maybe a satellite like that could detect that kind of oscillation. That's a great idea.
While we have this slide up, thanks for the talk, by the way. This has been great. But could you explain a little bit more about why magnetic fields suppress the L=1 mode?
Yeah, so it's basically, again, I didn't really go into the physics, but it turns out that it's the L=1 waves that can actually propagate into the center of the star like this. It turns out the L=0 modes can't propagate to the center at all. And the L=2 modes can do this, but they couple with much more weakly, basically. So basically the L=0 and L=2 waves are mostly trapped in the outer layers of the star, and they don't actually propagate into the core, which is where we think the magnetic field is. And so that means it's only the modes that propagate into the center of the star that are suppressed. And those are just the L=1 waves. So just those ones are suppressed. If there was a magnetic field at the surface of the star, then all the modes would be suppressed. And we actually see that in some red giants. Some of the ones that are rotating very fast, they have magnetic fields at their surfaces. And it turns out those help suppress all of the star's oscillations in some cases.
Where can we go to read your papers on this?
Well, you can go to my website. That has links to a lot of the papers, which I can put in the chat window here. You can also go, do you know about the archive? The Astronomy Archive? Basically, all my papers are on the archive, which I can give you a link to for anybody to download and read. So I will also give a link to the archive.
Appreciate it.
Yeah. So you can just search my name and some of these papers will come up.
Have you studied Betelgeuse, and did you get any interesting data during the most recent changes in Betelgeuse?
Yeah, it's a good question. I haven't personally studied Betelgeuse, but many other people are doing that as we speak. Yeah, so Betelgeuse had this big dimming event a few months ago, and I think it's still not really understood what caused it, but we think it is related to these pulsations. Betelgeuse does pulsate at pretty large amplitude. I think its period is roughly a year of its pulsation period. But those pulsations are somewhat random in the sense that their amplitudes change. So sometimes the star gets dimmer and sometimes it gets brighter. And there are epochs where it gets quite a bit dimmer. So people are still trying to figure out why Betelgeuse got so much dimmer several months ago. I know some of the thoughts are that it ejected some mass, and that mass condenses into dust, and then the dust basically blocks out the light of the star. So that's probably part of what happened.
Can this technique be used to study globular clusters and understand the structure of globular clusters?
So you could do this for individual stars in the globular clusters. There are some results on stars in globular clusters. They tend to be not quite as good because most globular clusters are pretty far away, and so the stars are dim, and so it's just harder to make the measurements. But you can do the same thing there, and it can be quite powerful because the stars in that globular cluster, we know that they all have the same age and the same composition, so it's easier for us to study them and figure out what their structures are.
Instead of doing focusing on individual stars as a focused on the whole.
Yep. Whole cluster, yeah.
Right.
Yeah, so that's basically what the Kepler satellite does. It measured the brightness of 100,000 stars at a time. So it didn't just do individual stars. And some, mostly it pointed in one direction for 4 years. And then it went into the K2 mission where it pointed in a bunch of different directions. And so there were some globular clusters in some of those pointings. And so there is some data for many stars in globular clusters. But like I said, it's often not quite as powerful because the stars tend to be a little bit dimmer. So you can't always get the signals that you're looking for. But there are some nice results on some of those clusters.
Got quiet there, Jim. Do you work with other astronomers, like in dealing with exoplanets? Like, I don't know if you're familiar with Dr. Frank Marchese over at the SETI Foundation.
No, I mean, I do work with other astronomers who study exoplanets, and I study a little bit of exoplanets myself.
Mm-hmm. Okay, I was wondering.
But yeah, I don't know all of them, unfortunately.
Okay, because I know he does. We do a lot of citizen science with the exoplanets with the SETI Foundation, with our new telescope, so a new digital scope.
Oh, cool.
Yeah. Thank you. I'm fascinated by this whole thing. You just really just blown me away tonight. I really are. Very impressive.
Astronomers are very creative because we study objects that are many light years away, that are very dim, that we could never travel to. And so if you want to learn anything about them, you have to be very creative. So you have to learn how to interpret this data.
Right.
In clever ways. Yeah.
When are you getting your doctorate?
Oh, I already have that.
Yeah, I kind of figured that, but it's just because it just says Jim Fuller. It doesn't say Dr. Jim Fuller. I was wondering about that.
Oh, yeah.
I was kind of thought you
were the doctor.
Okay. Absolutely. Anyone else?
Right. Any more questions? Okay. Well, gosh, thank you very much. This has been a fascinating talk, and this is a great way to just kick off our experiment with using Zoom for our general meeting. So thank you again for agreeing to give us this talk.
My pleasure. Thank you for having me.
Okay, so just a few. Curtis, anything else before we close this meeting?
I don't have anything right now. If anybody else has anything, go ahead and do it.
I'm gonna paste something in the chat. So the next general meeting is September 14th. We'll do that via Zoom. Okay, and for those of you who are interested in going to Lockwood this weekend, here's the sign up. And then the Lockwood committee meeting is on August 12th at 8 p.m. And here's the information on that. Andy sent out the announcement earlier. Let's see.
Is there a sign up for the pursuits tomorrow?
Okay.
Yeah, I was planning on going up tomorrow night.
There is not, but we can probably set one up real quickly.
Okay, a lot of us are going up there tomorrow night. I'm going up with Phil Taylor.
Yeah, I
Okay.
think I'll be up there as well.
All right, so we'll go ahead and I'll go ahead and coordinate with Kevin. We'll clear out the current sign up and then reinitialize it for the Perseids. Okay.
I wish
Yeah,
we could pause to Jim Fuller, to Dr. Jim Fuller. I wish he could see her. So I don't know about anybody else.
Thank you very much. Thank you again.
Hi, Zoe.
Yes, thank you all.
Jim, why are you blurry?
Oh, that's because there's some sort of leak inside of my computer, and so the webcam has some fuzz on the inside of the computer.
Oh, I was going to tell you, Dr. Fuller, you've been oscillating there all night, and I keep thinking that we should measure that and see what kind of music your images play.
No,
you look a little bit like Max Headroom with almost ghostly image.
Well, I wish I had a more satisfying explanation, but no, it's just that.
That's fine. Fuzz is good.
Just that my lens is dirty, basically.
Okay. All
This was
right.
great.
Thank you, everybody. You can check the YouTube channel for this meeting. It's been recorded. So thank you very much.
Okay, thank you all for coming to the meeting. I'm glad it worked out the way it did.
Yeah, Jack Eastman here in the high country of Colorado, and I want to thank everybody. The Zoom thing worked fine. Dr. Fuller, you get both thumbs up. And Mike and Jinky Gardner, good to see you.
You too, Jack.
Great.
Good seeing you.
I'd have the camera on, but I want people to think I'm the worst housekeeper in Colorado rather than turn the camera on and prove it.
Jack, put your Clark in the background.
That's in the background.
There you go.
Get yourself a virtual background.
Yeah.
Hey, we have another shootout at, my big Clark got a little sister.
Oh, did you get another one?
Yeah, I picked up a 3.5 inch dated 1870 here at the end of last year.
Wow.
I think I posted something to the bulletin about that. I don't And it was a giant pain in the butt. For some reason, Gmail likes to delete pictures when I try to send them.
Yeah.
It took 3 tries.